Hi everyone, it's your SI leader Noora here to discuss hydride shifts. So what is a hydride shift? A hydride shift is a basic type of carbocation rearrangement that can occur to make your intermediate carbocation species in a reaction even more stable. So here you have a typical hydrohalogenation reaction drawn out for you. I started with my alkene species and I reacted my double bond by picking up this hydrogen and taking this region of electron density that was in the covalent bond between my hydrogen and my bromine and kicking that off onto my bromine, producing a bromide anion. Now, what type of carbocation intermediate are we going to produce from this reaction? Now, I'm going to add my hydrogen at this point of what was my double bond, producing this carbocation species with a positive charge centered on this carbon, more neatly like that. And the reason I did this is because I know that this carbocation, because it is attached to two other carbons, is going to be a secondary carbocation. Versus what would happen if I attached my hydrogen at this point, I would produce a primary carbocation with my positive charge centered over here. And you do not see that in any of your alkene reactions. Again, that's because your secondary and tertiary and anything is really more stable than your primary carbocation. So I know that I want to proceed from this point. So we have our secondary carbocation intermediate. But what can we do to make this intermediate even more stable, even more favorable? And the answer lies with this hydrogen on your neighboring carbon. And we're going to do a hydride shift using this hydrogen on the carbon directly neighboring our carbocation. So what's going to happen is this hydrogen is going to shift over onto that carbon atom, producing this species. Again, I'm going to keep my colors consistent. This is the hydrogen that we just used for our hydride shift. This is the original hydrogen that we added across our double bond. And now our carbocation is this region right here, centered. The electron deficient region is on this carbon right here. And again, this is a carbon attached to 1, 2, 3 other carbons, making this a tertiary carbocation. So our hydride shift has served to make our intermediate even more stable. And what you're going to see with hydride shifts is, again, this system where you're moving from a secondary to a tertiary carbocation going downhill, going from something that is more unstable or more higher in energy to something that is lower in energy and thus more stable. And that's what is meant by a downhill process. You're going downhill in energy and you're going to something that is more stable. So another thing I wanted to point out is that I used an irreversible reaction arrow for my hydride shift. So once you shift your hydrogen, you're not going to want to switch it back or flip it more than one time. In these problems, you're only going to see one carbocation rearrangement occur. Same for your methyl shifts, only shift it over once, don't do anything fancy, and move your methyl or your hydrogen around multiple times. So continuing our reaction from this point, we had our bromide anion hanging out over here. It's going to attack this electron deficient region, producing our final product, which is right here. And again, just for clarity's sake, I'm going to redraw all of the changes we made to our original molecule. The hydrogen that we added from our original addition reaction, the hydrogen that we used in a hydride shift, and the bromine anion that attacked at this point, producing this final species. So there you have it, hydride shifts